So we'll just start this one from the beginning, and then I will explain the problem that will be like this on the final exam. I don't see, it doesn't make sense for us, I don't think, to meet on Wednesday and Thursday. I mean, this will probably work okay, but we're just doing an example. Because what I've got left is I want to review the graded exams with you, and then I just want to do a review of the course. And that's all we have left. So what we could do is a week from today on the last day of classes, which is still weird to say. Like, why are we having classes during finals week when you have finals the very next day? Is we'll just go long on that day, I think is the easiest way to do it. And we'll have everything covered. So we could probably take Wednesday and Thursday off. So if you don't hear from me, we're not meeting on Wednesday. So let's start this out. So with this flow, it enters this frictionless adiabatic supersonic nozzle. So all of this, all we had time for in compressible flow was to do the isentropic flow, with the exception of a shock wave. Okay, so frictionless adiabatic would mean the isentropic flow. Converging, diverging. So you want to start with that. So get a good sketch of a converging, diverging nozzle. Wait, this was my new marker. What happened? It died. Oh my! I literally just got this marker on Thursday out of the front office. We'll see if this one's any good. No, that was not good. Maybe it's the board. What did they put on the board? That's slightly better. There, we'll go with the black marker. I got a feeling there's some film on there. Alright, let's get our converging diverging. Alright, so somewhere down here we've got a shock wave. And we got our exit. So you can think of this section as being like one. There's your throat, X, Y, and the exit is in 2. Shock wave, we always use the nomenclature in X and Y.
Can you explain the X and Y? Why are you using X and Y as linear, I guess?
Good question. You'll have to ask somebody from like probably 1952.
Okay.
Yeah. Somebody decided across the shock wave we're gonna do X and Y. So I guess so they didn't confuse it with the other points. I don't know. It's the nomenclature that's in the textbook and in other textbooks, so that's what we're gonna stick with. Okay. So we got a shock wave position, normal shock wave position, the diverging portion. Cross section right there is 0.1. Local Mach number right there is also 2. Upstream of the shock. Upstream would be this way before the shock. Downstream, after. So we've got some properties of stagnation pressure, 200 psi, stagnation temperature, 1200 degree range. And then finally, we got the exit area down here, 0.15 squared. And that's everything. So, I'm thinking about this problem as two separate things to solve. There's the stuff that happens up to the shock wave, and the stuff that happens after the shock wave. Okay, so in fact, the problem you'll have on the final exam, I'm actually going to split it into 2 problems, even though it's one complete same problem. I'm going to do the first part where you have to solve for this stuff up to what would be a shock wave. And then for the next part of the problem on the next page, I'm literally going to have that exact same duct with that shock wave where your end point was before, so you can start working across the shock wave. That way you can kind of compartmentalize what you're doing and what tables you're going to. For this one, I'm going to do it all in one shot. So part A, we talked about this one on Thursday. What's the Mach number at the throat? Now, it's not guaranteed that the Mach number at the throat is going to be 1. That is the only place that it could happen, at the area minimum, okay? But it's not guaranteed, so we have to look at what clues we have. If there's a shock wave, then we know that this section had to be supersonic, had to be above 1. And the only place that 1 could have occurred is right there. It says enters, it actually doesn't even say that it enters, yeah, at subsonic velocity. So it enters at subsonic velocity. So we know that it came in at Mach number less than 1. And we know that here it has to be Mach number greater than 1. In fact, it tells us it's 2. And so that means it has to be 1 at the throat. So make sure when you delineate it's 1 at the throat, make sure you justify it. Mach 1 at throat, since the shock indicates supersonic downstream, and entered subsonic area medical has to be 1. Okay, part B. So I started going through this one again on Thursday. Let me get this a little bit more clean this time. So the first thing I want to do is take what information I know, Mach number 2 right here, and I want to go to table DI that I have right here. And I want to get the area ratio at Mach 2. Very last row down here. Keep in mind these are 2 columns. Last row. And I will be able to get from that the area ratio. 1.6875. Okay, here's the important advice. Label everything. So right now we're on the area on the X side because Mach 2 has to be on the upstream side. So my area ratio on this side is going to be from table DI 1.6875. We're given the area right there, so I can plug that in right here. My algebra there, solve for A star, and I have the area at the throat. What's done? Part C. What is the exit temperature? Okay. Now we need to start working on the other side of the shock wave. So I want the area, I've got the area at 2, I want the temperature there, and eventually I'm gonna want the pressure there as well. So to take care of this, we are now passing through the shock wave, so I'm not going to use table DI. I have to use table DS. Table DS starts at 1 because there would be no shock wave without being above Mach 1. So when I come down here, Mach 2, I got 0.5774, and I'm just going to round that. So on the other side of the shock wave, it drops below supersonic, and we're at 0.58. Now I can take that go to DI to learn the new stuff on the other side of the shock wave. Everything has now changed on the other side of the shock wave, except for one thing, which we'll get to in just a second. So at Mach 0.58, I come here, it's between 0.55 and 0.6, and I can actually get my temperature ratio and my area ratio and a whole bunch of other stuff. So let's see, I'm gonna start with my area ratio. So we're 1.25 or 1.18 in between there. We're actually almost smack in the middle. So it turns out that it's about 1.2. Okay, so because we went through a shock wave, Our old area ratio is 1.6875. We're now at a new Mach number, so we had to look up our new area ratio. Now, what this means is, there's our original supersonic nozzle. This A star doesn't apply to this anymore because we're on the other side of this shock wave. So this new A star would be if we took it down to a new throat, and that would be the size we would need to get back to Mach 1. Now, I'm putting that dotted line because we're not actually going to do that, but this is gonna be our new reference, okay? So, I take that, I know the area at, AY, so I can plug that in, 0.1. I'm gonna label this as A star new. 1.2. And we'll solve for A. Okay, why did I do that? Because I need to know stuff at the exit of point 2 right here. So with that, I can now get my new ratio at A2. And what was it? It was 0.15. I'm not passing through a shock, so I'm still on the table DI. I can scan down and find a 1.8. Now this is where we have to be cautious because there are two 1.8s on this. There's a 1.8 up here at around 0.3, and there's a 1.8 right up here at about 2.07. Which one do I use? You're going with which one?
The first one.
You're going with the first one, you're going with below the speed of sound? Okay, this is where you have to remember what's happening here. We are below the speed of sound now, because we're on the other side. It's expanding, so we are getting slower. So you're spot on. Let's see, what's it work out to be? Our Mach number at the exit is 0.34. So in between those two, we were at 1.8. So 0.35 was 1.78. 0.4 was 1.6. So we're closer to the, sorry, between 0.3 and 0.35. 2.0 and 1.78. So we're closer to the 1.77. So it gets us to 0.34. You can always use the equations instead of that table. You can interpolate, you can do linear interpolation between those two if you want to. But I just kinda eyeball it, get close enough to the ballpark. Just double check yourself, cause I just now did exactly, was off by 1. Okay, so now that we have that, we're gonna wanna grab the other stuff that we need to actually finish solving this part of the problem. So while I'm there, I'm gonna look at my temperature ratio and my pressure ratio, cause I'm gonna need that for part D. So 0.98, 0.97, 0.93, 0.91. Again, you can use the equations if you don't wanna use this table, but this is what they are. T2 over 0, 2. I picked up about 0.97, and I'm gonna grab my pressure ratio now, because looking ahead, I need it for part D. 0.92. Okay, I'm almost there. This whole point in this part C was to solve for the temperature at the exit. Solve for the temperature at point 2. That means I need stagnation temperature. Good news. There's one property and only one property that does not change through a shockwave, and it happens to be stagnation temperature. Yay! And we already have that, it was given in the problem statement, so we can plug that in at this point, and we are good to go. Okay, part D. I have this to figure out what the exit pressure is, but I don't know P stagnation at the exit. So I need to figure out that number right there, we'll do the 0.92 and I got it. So to do that, I'm actually gonna have to revisit the shockwave. I'm gonna have to go back here and figure out what's our new stagnation pressure on the other side of the shockwave. I have it on the X side, don't have it on the Y side. So I actually have to go back to the shock, and go to this table, back when we were at Mach number 2, come over here, and it just so happens, I've got a pressure ratio right there. Let me make sure I got that right one. Oh, I wanna get on the other side. Let me make sure I got this. Oh, even better. We've got a ratio of, you won't be able to see this probably on the video, but it's a stagnation pressure on the Y side divided by the stagnation pressure on the X side, this column right here. So I have the ratio of stagnation pressures. So I can take my Mach 2, come over here, and it's 0.72. That's from DS. Excellent. I have PO effects, so plug that in. 200 PSI. Oh, I put that on the wrong side. It's on the bottom. Okay, now be careful on the finding, okay? I asked for the static pressure, just the regular pressure. I didn't ask for the stagnation pressure, so you're not done yet. And there's always a temptation with about a quarter of my class that says, oh, I'm done. Nope, got one more step here. So we go back to our P2 or PO2. Which of course is POI, stagnation property or isotropic properties don't change except across the shock. So I can plug in the same thing. 144. And just grab my 0.72 from over there, or 0.92 from over there. 0.92. And solve. Okay, so usually getting pressures on the other side of the shock is a little bit trickier than getting temperatures because of the fact that stagnation temperature stays constant. Whereas with pressures, you gotta get a new reference pressure and then you're good to go. Part E, what is the mass flow rate? Multiple equations that were given for this one. I'm gonna use this one for reasons unknown, just because that's one I grabbed. I know a lot of what's going on at the exit. Now, again, conservation of mass still applies, so the amount of mass going through the throat and across the shock has to be constant. Unless the flow is choked, well, it would still be the same coming in, I guess. Choking is okay as well. I'm using this because I know all kinds of stuff at the exit at this point. I saw the exit. You can plug in the numbers at that point. Air is 1.4 for the K and 1716 foot pound per slug degree range. And then just plug in your air, everything else. Make sure your units all cancel out. So I got a 144 in there. I got a 1.5 for that. I got a 0.34 for my knock number of my knock room. But you've got all these numbers. You just solve for it. So make sure everything cancels out so you get a mass flow rate of 0.81 slug per second. You can obviously change that to pound mass if you wanted to, but you don't need to. There you go. You could just as easily have used E over RT area, Mach number, RTK. Another formula that was given. You got all the numbers for that too. So just rearranging everything however you want. So let me recap what's going on here. I'm given stuff for the X side. I can use that just fine when I start to analyze, I guess, right away almost. Working upstream. So I'm able to get that area of the throat. I'm only working for BI from that. Part C, I'm gonna have to now switch to this other side of the shockwave because I'm now looking for properties at the exit on the other side of the shockwave. So now I'm gonna have to start using DS, but as soon as I get my stuff on the other side of the shockwave, I have to start using DI, and then I'm good to go. The key in this is, if you get off track, it's usually not too big of a deal. You're probably on the right table, you're just grabbing stuff you don't need. And you kind of hit a dead end. You'll be able to backtrack, go back and get what properties you need and work through it. In my opinion, this problem is slightly more difficult than the one I'm gonna give you in the final. Ultimately, they're identical. It's just that I might instead give you a pressure and you'll have to find the stagnation pressure. I might just swap it, so you'll be working backwards, if you will. I think this one's a little trickier because you gotta go through all this mess to find your new throat area that doesn't actually exist downstream. So you can backtrack to DI and find your new Mach number. So it can get a little convoluted, but otherwise that's it. You're just going back and forth between these tables, looking things up. I do want to be clear that these tables are only for air. I'm going to give you an air problem, so I'm not going to fool you and end up giving you something a little bit different. And you can use the equations instead of the table to get more precise answers. It just takes a little longer, unless you've got a mic programmed in your calculator or something, which I don't mind if you want to do that, because they're just a constant equation. Put in your two properties and it can spit it out if you got a programmable calculator. So these are based on the equations. It just so happens they're using the K for 1.4, which is air. So I'll give you an air problem. You don't have to worry about that. Now, with that, since we're already rolling, I think I'll start a fluid mechanics review, just the entire course. We'll start a little review, see how far we get, and then we'll finish up the rest of it when everybody's back in person next Monday. So let's use our last 20-ish minutes to get started on our review. And I do happen to have that up. I'm going to do this in outline style. Is there any questions that you guys are worried about on this stuff here?
Is the 144 to get inches into feet?
Yes, it is. Yeah, since I was trying to shove it, I didn't want to erase anything yet, so I tried to shove it in this corner.
Mm-hmm.
So I didn't put my units on the top, and I kind of wish I would have, but I just didn't have this would be PSI. Everything's absolute when we're dealing with compressible flow. Oh, and by the way, the last thing I wanted to say about this is, one thing about compressible flow is it's much more approximate than what we were doing even with the energy equation and Bernoulli equation. Like, that's probably not actually gonna be your exit temperature right here, 1160. And the reason being is because we're using isotropic properties. In real life, there's gonna be friction in that tunnel. And so if you are interested in taking that next step in a compressible flow, which is actually pretty interesting, and again, not that hard. Once you get the basic concepts of physics down, the mathematics and solving problems is pretty easy. But we would add in friction, that would be called Fano flow, and we would add in heat transfer, because if we go back to that problem, it says adiabatic and frictionless. So when you add in heat transfer, it's something called Rayleigh flow as well. So you can get a little bit more into that if you want to take the applied fluid mechanics course, which is offered next spring. So they should cover most of that entire compressible flow chapter. We only did half of it. All right, I'm gonna do this outline style. So I'll have the slides there to reference where we're at. Basics, so we'll call this I. Roman numeral 1. Throughout this semester, we were keeping inventory of length, time, mass, or length, time, and force. Why I wrote it this way, I don't know, because most of the time we were doing MLT or FLT, but that's what I wrote on my notes. And that comes into big time play when we get into dimensionless numbers. So, what really resonates with me about this mass versus force thing is when you gotta go back and forth from 1 pound force to a pound mass. And so if you use slugs, I can never remind people this too often. If you're using slugs, it's a 1-to-1 converter. So it would be fairly simple to convert. On the flip side, if you want to get to pound mass, you got to use that 32.2. And this is a unit conversion, only because we happen to live on Earth. That would be a different unit conversion if we lived on the moon or some other planetary body. And that comes from F equals ma. There's your acceleration of gravity. There's your mass. All right, specific weight. It usually takes some students most of the semester to get down this concept between specific weight and density. And you can interchange back and forth by just using that constant of gravity. And that's why we end up having like 3 different forms of the mechanical energy equation, because you can either use density or you can use specific weight. And then specific gravity is just from a reference. So if you need to look up your density of the fluid, then you just use a reference of density of H2O at 4 degrees Celsius. And you can do the exact same thing, since it's just different by a constant. You do the exact same thing with specific weight. Ideal gas, keep in mind its name. When you want to pull it out of a hat and start using it, it's got the word gas in its name, ideal gas. I've seen students try to start using this on a liquid. Don't. Use absolute temperature with that. So that's why in the compressible flow material that we just finished up from chapter 11, everything was in absolute pressure, absolute temperature, because those calculations came from ideal gas law. On the flip side, when you're doing the mechanical energy equation and the momentum equation, I recommend using gauge pressure, okay? Not absolute pressure. Especially the momentum equation. Don't try to use absolute pressure in the momentum equation. You will get the wrong results. Every once in a while might get lucky and the problem's a little simpler and it works, but I cannot solve the exam problem that you had on exam 2 with the momentum equation with absolute pressure. I can't get the numbers to come out right. And the reason is I'm leaving some atmospheric pressure out somewhere, and I never know where, because it's acting around the whole body. So momentum equation, gauge pressure, ideal gas law, compressible flow, absolute pressures. Okay, let's see, viscosity. Okay, so it comes from Newton's law of viscosity, which does not apply to mayonnaise. The greatest way to think about this is take a moving surface and take a stationary surface. And when you pull that fluid, it's stuck to this surface and it's stuck to that surface. So you end up pulling it out. Now, it's usually not going to be linear the way I drew it, except at small scales, which is why this is not delta U over delta Y, but it's du over dy, because it's at a very small scale. So if this were a very small distance, you'd see this little linear proportion. And so, that's where viscosity comes from. Depending on what type of fluid this is, depends on how that thing shears. And with that, you can always use kinematic viscosity, because it's just difference by its density. And that is very handy in the Reynolds equation. And that takes us to our first chapter that we solved problems, was fluid statics. Which actually is chapter 2. You got a fluid at rest, pressure at a point is independent of the direction. Okay, so pressure looking from the bottom to the top, all the same. This is why I said don't use the absolute pressure with the momentum equation, because when you use absolute pressure, you got atmospheric pressure to deal with. When you got atmospheric pressure to deal with, the pressure at a point is independent of the direction. And so it's like, oh, I forgot that there was pressure coming in from the top from the atmosphere, or from the bottom from the atmosphere, or whatever, so I leave it out, so. For fluid statics, that comes in handy because, when we look at pressure variation, we know that the pressure in a static fluid does not vary in the horizontal direction, horizontal to gravity, but vertical with gravity, we've got ourselves a change. And if it is a linear change, then we know the function here, and we can integrate that and solve for pressure difference between the two points. And for those of you that were struggling with a pump curve or pump table when you were looking up pumps for your projects, almost always those pump curves are given in feet or meters, right? So it's given in head, and so hopefully you are astute enough if you needed to just do a quick convert to pressure. So just multiply head times gamma, do your convert. You're there. So the other thing after we did this pressure variation stuff is we looked at manometers and then we looked at manometers. We looked at both. We didn't do much with the manometer. But the manometer, the key here, manometers are really, really easy to me because I use the manometer rule. So use that manometer rule and you'll be in good shape. that three-step process. And then, so that was A, I'm gonna label this B, pressure variation. This is your subject number C and D. So once we figured out pressure variation up and down, we can start to solve for forces. So the reaction force on a plane surface is a fairly simple formula. The difficulty comes in the geometry and trigonometry, right? Because you need to get the centroid, and the centroid in the H direction could be different than the centroid distance in the Y direction because it might be at an angle. So get your angles right, get your sines and cosines right. So this is the hydrostatic force on a plane surface. To get its location, it's a little trickier because you gotta use that IXC, and that comes from the table in chapter 2. So you need to look that up. Go to chapter 2, you might want to put a little tab in your book on that. On exam number 1, I actually supplied that table for you, now you don't have to look that up. Okay, so see the major difference here, right? If that plane surface is at an angle, HC follows the direction of gravity, YC follows the direction of the plane surface, okay? If you're lucky, you got a vertical surface, and H and Y are the same. If I were to give you a curved surface, and I won't, you'd have to do projections. Curved surfaces take too long because you usually have to integrate to get your centroid of the volume. So I don't want to eat up your time. But you just project the X direction and project the Y direction, and you're basically using the same formula. And then the last topic we had in fluid statics was buoyancy. And buoyancy is actually that vertical component. So you don't want to do both, do one or the other. Basically, the weight of the fluid above it. Or the imagined fluid above it. Alright, that gets us to, I'm gonna skip chapter 3 for right now. Now, what was chapter 3? Bernoulli equation. Why am I skipping it? Because it's out of place intentionally. It actually belongs with the control volume stuff we did. Because the Bernoulli equation is just a specialized form of the energy equation. So it really belongs in chapter 5. We put it up front in the book so that you can actually solve a couple of real moving fluid problems and get your mind in the game before we hit chapter 4, which is fluid kinematics. So I don't want to write all this on the board because I tend to write too fast on a very slick surface and you can't hardly read anything that I write. This, hopefully you can read this. So the things we talked about with kinematics basically got our head further into the game after we tried out the Bernoulli equation. It said things like, wait, when you're doing the Bernoulli equation, you're actually focusing on a volume. If it's a streamline, that volume could literally just be the volume around the streamline, right? Point 1 to point 2. We cannot do Lagrangian in fluid mechanics because trying to follow a particle of fluid could be impossible. It's spinning, it's breaking apart, it's stretching. It's even changing volume if it's a gas. That ain't gonna work very well. So we do the focus on a volume, that's what we're gonna use. The next thing we talked about was the level of detail we want to take. And these were the two main points that were made on the quiz that you took. We can look at human-sized volumes, or we can shrink down to a infinitesimal point. And so, control volume, chapter 5 material, momentum, energy, continuity. Differential, that crazy thing with all those partial differential equations. That starts to get into graduate level work. So we just looked at it, we didn't solve any of these problems. We did learn a little bit about George Gabriel Stokes. Streamlines, we tried out streamlines with the Bernoulli equation. And then we actually looked at a further definition of what they were versus a streamline versus a pathline. The important part is this. You're usually dealing with steady flows, and with steady flows, all three of these things are the same. With an unsteady flow, they will actually look different if you use like smoke screen or whatever. Now, to be able to use this point of view, Eulerian, we had to convert the equations that you've been using since you were like probably a freshman in high school. Because F equals ma means that you're following the particle mass. So by the time we ran it through the Reynolds transport theorem, this doesn't look anything like this anymore. And in fact, it looks like this. Sum of the forces is equal to the momentum rate out minus the momentum rate in. It's a rate equation. So Reynolds transport theorem did that for Newton's second law. It did it for the energy equation, conservation of energy, and it did it for conservation of mass. And when we were done, we had our three equations that we'll talk about on the next slide. Eulerian derivative converts our equations for the differential stuff, and it gave us the Navier-Stokes equations, and we all ran screening for the x's. So that gets us to 3 and 5 put together. So since this would have been Roman numeral 3, I'll start with Roman numeral 4. Control volume analysis. Continuity equation. If we got uniform properties, so we don't have variation in velocity or density over our area, then it's really simple to say, I'll sum them up. The mass flow rate out is equal to the sum of the mass flow rates in. Or mass flow rate, rho P A. Yes, there is an integral form of this, which you only need to integrate if your properties are varying across your outlets or varying across your inlets. So that you can basically the sum of those. That's A. B, for some of you, 4B is your nemesis. And for others, you're like, nah, I got this master. I got this down. Linear momentum. Ooh, it's ugly in its original form. When you've got all those integrals all over the place, you know, it looks something like, let's see, we take this contents of the CV for forces, and then I'm going to say, oh, what if it's unsteady? You gotta worry about that too. Then I gotta worry about all the way around the boundary. I'm going to put that in parentheses because it's velocity in the x, y, or z times the mass flow rate. This one we didn't deal with because we didn't worry about any any changes with time. So what we usually did is uniform properties across the areas, so we didn't have to worry about integrating. So we ended up with the glorious form . First part depends on whether it's an outlet or an inlet. Second part, the vector, u, v, or w, depends on the axis. That'll get you your zones. Looking back on this after like a month or so, you're like, oh. The forces we usually deal with is the actual reaction force you're going to be covering. Pressures times area, that does depend on direction, plus or minus. And then we did did not do shear stress, but we sometimes did the weight of the fluid. And that's it, that's your momentum equation, not bad. I got 2 minutes, I can get the mechanical energy equation in there. Now this one, you have likely gotten very comfortable with by now, because not only was it used throughout this chapter 5 thing, but it is the pipe flow equation. When we were using this one, I hadn't yet defined how to look up the GHL stuff. So I was just giving it to you. You now know where all that stuff comes from. Friction factor, compound forces. And that is a fantastical place to stop. So, Monday, so if you don't hear anything from me on Canvas, we will not be meeting on Wednesday or Thursday, so you can use that time to actually get other projects, reports, studying done, or you can sleep. You just leave DME and sleep. That sounds like a good plan, actually. And then, we'll meet on Monday. I will finish the review, and I will review the graded exam. And that should be everything. And then any questions you have, which I actually should be able to maybe do it. So we got all caught up, and got so caught up, we made up the time for those that are in New Hampshire national playoffs. People just didn't come to